One thing to remember before we start deriving the equation is to keep track of signs, the distances, So the convention that is followed in this case is that distances to the right are positive, right of the pole are positive, and distance to the left of the pole are considered negative. And then heights measured above the central axis, above the principal axis, are considered positive, and heights measured below, so in this case A prime, B prime, would be considered to have a negative height, and AB has a positive height. The radius of curvature of this mirror, because it falls, the center of curvature falls to the left, is considered negative. And in the example on the right, for a convex mirror, the center of curvature falls to the right of P, and therefore the radius is considered to be positive. The object and image are both positive, both have positive heights in this case, because they're both upright and located above the principal axis. Okay, so let's move on to the derivation of the mirror equation. To begin with, we'll look at the concave mirror. Let's look at these two triangles highlighted in blue and green. And this is not exactly a triangle, but for axial rays, again, we're going to consider MP as more or less a straight line. So we're going to think of MFP as a triangle. And what you notice in these two triangles is this angle equals that angle, vertically opposite angles. And this angle right here is a right angle, and so is that angle there. That's a right angle. So these two triangles are similar. It means their sides are in proportion. So we can write that as A prime B prime divided by B prime F equals, so that's this length or that length, equals MP divided by PF. MP divided by PF. And now let's look at two different triangles. Let's see. We're going to look at that. And I need to take care of this part here. Okay, so now we're going to look at ABP and A prime B prime P. So in these two triangles, again, you have right angles. Both of these are right angled triangles. And this angle here, because the incident ray makes the same angle with the normal as the reflected ray, so this angle is identical, is equal. So these two triangles are also similar, and for these two similar triangles, then we can write down this relationship, AB over BP equals A prime B prime over B prime P prime. And so now if you look at these two equations, first we'll replace MP, that is this distance, with AB. Remember, we are saying that MP is almost a straight line perpendicular to the principal axis, so MP then equals AB. So let's write that down. This A prime B prime by B prime F equals AB over PF. And again, I'm going to do a bit of algebra here. So let's take AB down here to the denominator. A prime B prime divided by AB equals B prime F divided by PF. And over here, if I were to look at what is A prime B prime divided by AB, A prime B prime divided by AB, that is going to be equal to B prime P prime divided by BP. So we have two expressions for A prime B prime divided by AB from the two sets of triangles, two sets of similar triangles. So we can write, that this quantity must be equal to that quantity, since they're both equal to A prime B prime divided by AP. So we can write this down as B prime F by PF equals B prime P prime divided by BP. Now let's write these in terms of the object and image distances. The object and image distances. So the convention that is followed is that the object distance is denoted as U. The image distance is denoted as V. And we have already seen that the focal length is denoted as F. That is, the focal length is denoted as F. So let's see if we can write these quantities in terms of U, V, and F, keeping in mind the signs, the appropriate signs, positive and negative. We're looking at this equation right there. What would B prime F be? That is just the same as BP minus FB. If you look at the diagram here, B prime F is the same as B prime P minus FP. And BP is, there should be a B prime here, B prime P. B prime P is the image distance. And if we want to write it as V, but remember V is a positive quantity, while we have determined that distances to the left are to be considered negative. So we'll have to add a negative sign here. Minus FP. What is FP? That is the focal length. And again, since it's to the left, we're going to put a negative F in front of it, a negative sign in front of it. So that just equals, the two negatives cancel out. You've got F minus V. And that is, what is B prime F? Now, what is PF? PF is the focal length. We've already determined that. PF is just negative of the focal length. What is B prime, P prime? So it looks like there is no P prime. I've made an error here. That's just B prime P. Need to take care of the prime there. There is no P prime. Okay, so what is B prime P? B prime P. B prime P is the image distance. We've already seen that here. B prime P is negative V. And what is BP? BP is the object distance. And again, since it's off to the left of the pole, we're going to write it as negative U. Now, if we substitute all these quantities in here in this equation, what we have is B prime F, that is F minus V, divided by PF, that is minus F, equals B prime P, that is minus V, and BP, that is minus U. And so if we were now to simplify this relationship, let's get some more space here. Okay. So we have F minus V. Actually, I'm going to write it as V minus F divided by F. So I've got the negative sign taken care of. Is equal to V over U. The two negatives cancel out. And so writing this again as V by F minus F over F is 1 equals V by U. It's dividing both sides by V. What we get is 1 by F minus 1 by V is equal to 1 by U. And then if I were to take this over to the right hand side, I would get 1 by V plus 1 by U equals 1 over F. That is what is called the mirror equation. The mirror equation.